Yes.
So for our next Rachit will tell us about succinct randomized encodings.
So hi everyone, I'm Rachit, and G has done all the hard work for me, and I'll just use the primitives that he used to maybe show something cool. So this is succinct randomized encodings from Laconic function evaluation. This is joint work with Nir Bitansky at NYU. So let's begin with what are randomized encodings. So this is a beautiful object introduced by Shai and Koshilevitz, and the idea is as follows. Imagine you have an input x and a function f, and you wish to compute f of x. But you want this computation to be much simpler than just computing the function itself. So this encode functionality should be simpler than just running f and computing x on f. So once you have this encoded computation, you want correctness, which says that given this f tilde of x object, you can decode and get back the original computation, f of x. And this decode computation will be as complex as f, but what we're concerned about is optimizing this encode computation. And there is a security property which basically says that f tilde of x should only reveal f of x. So what you're not allowed to do is like this encode function cannot just simply say output f comma x. So it should only reveal f of x. So this notion has been studied for a long while, starting from Yao, and it has applications in low parallel time or low depth, and like other areas of cryptography. This depends on actually which functionality. So what do you mean by saying something is simpler than just running f? So if I talk about parallel time, then there are these applications. But if I'm trying to optimize encoding time, that's the notion of a succinct randomized encoding. So let me just talk about, this is what we are going to focus on this talk. So in a succinct randomized encoding, you have a Turing machine M. So instead of thinking of a function, now I'm going to think of it as like a Turing machine M, which runs on this input x for time steps t. What we want this encode functionality to be simple is this encode should run much, much faster than time t. And it should output this m tilde of x. And decode could take approximately t time, and it should output m of x. So this is the notion of, yeah?
There's another way to interpret succinct randomized encoding, which is the encoding size is small, but running time still goes with the complexity of the computation. So maybe better to separate these two different names.
Okay.
Let's call succinct the gobbling, and then the succinct.
Yeah.
No, randomized encoding and gobbling, the difference is gobbling has a specific input format. Randomized
In
encoding
general, the
doesn't.
term succinct is overloaded also proof systems, right?
Yeah.
Succinct Turing machine.
So they have a different terminology for time succinct.
Yeah, time succinctness and the size success will be different. Yeah.
Yeah.
That's my point.
Okay.
Yeah, well, maybe succinct by default means both.
Okay, I'll add more adjectives to things, and then but we'll stick with succinct randomized encoding for this talk. And so correctness has this property that decode with m tilde of x can lead back to m of x. And security, again, says the encoding only reveals m of x. And the way it's formalized is a simple like security experiment where either you're given m tilde x or the simulator is given m of x, and you're asked to distinguish between the two worlds. So any questions about this notion? Okay. So this notion has a lot of applications, and it was studied in 2015. And one of these applications is time lock puzzles. So time lock puzzles are these cryptographic objects where you can sort of lock a puzzle message for a certain amount of time, and nobody else can open the message until that period of time has passed. So you need a lot of sequential computation to open this time lock puzzle. And these are applications which we either only, time lock puzzles we either know from like succinct randomized encodings or like from a specific repeated squaring assumption based on RSA. So these are like sort of strange candidates which we don't have a lot of, strange primitive which we don't have a lot of candidates for. I'll talk
about the encoding function, because sometimes I saw that you want to separately encode x and separately encode m, but here you allow the encoder to know both of them.
Yeah, the encoder knows more.
So for applications, it's okay.
Yeah. So I'll talk more about time lock puzzles later in the
You can consider
universe.
randomized encoding to be decomposable, where the input is consists of two parts, and then the function description can be thought of as one part of the input. And
But you're saying the modern one is not decomposable.
You can compose it with a standard garbage link to make it decomposable. Usually you can get the decomposability essentially for free.
On the gobble circuits.
And Rachit, I should think about fixed length input and a single bit output.
Yeah, for this talk, single bit output is fine, a fixed length, but yeah. Okay, so it has applications to delegating computation. So imagine you're some client who wants to run like a very complicated machine learning algorithm on your secret data. And what I could do is I could produce a succinct randomized encoding, which took me much less time to compute, and I can offload it to the server, and the server can perform this extremely complicated computation for me. In general, it's like an important tool, like randomized encodings in general, like they show up in MPC use cases where instead of like sort of performing MPC over the original function or the original Turing machine, now you're going to perform like MPC over this encode functionality, and that gives you a lot more because now your parameters only depend on the running time of encode, so it gives you a lot more communication or computation efficiency. And it also has been used in obfuscation context, where it's been used to go from obfuscation for circuits to obfuscation for Turing machines. And in general, like this notion is kind of surprising. I have some like slides for open work of how it's related to obfuscation, and we'll get there. Okay, so let me just maybe answer some of the questions about time lock puzzles, because I think I saw like there was a slide for the open questions at like I think somebody had posted like there was a session on open questions, and there was an open question: can you build time lock puzzle from lattices? So we actually can, and prior work shows this. So I was like, maybe I'll explain that like succinct randomized encodings imply time lock puzzles. So what are these time lock puzzles objects? So imagine there's a generation function which has this message m and some time t, and it outputs this puzzle. And there's a recover procedure from this puzzle. Anybody can recover m. But the constraint that we have, this generation puzzle should be much, much faster than time t. And recover, this is different from the succinct randomized encoding, where we require that recover should be slow. So succinct randomized encoding say nothing about the decode time, but here we say like an adversary who even has like a lot of parallel power should not be able to recover this puzzle in much faster than time t. So naturally, like in a work in BGJ plus in 2016 showed that succinct randomized encoding plus some worst case non-parallelizable language ends up giving you a time lock puzzle. And just to explain what this worst case non-parallelizable language is like you can think of like a hash function on top of hash function multiplied to a long time. So it doesn't, you're not cheating. You're not saying that like this already implies a time lock puzzle because this does not have like a fast generation constraint. So this might take you a long time to compute in general. So the fast generation comes from this like succinct randomized encoding part. And it's somewhat necessary because time lock puzzles imply this sort of worst case non-parallelizable language notion.
The point is that it's worst case.
Yeah.
But even average case would make it easy, right? Even if you have an average case non-parallelizable language, it wouldn't make the problem easy.
So you need succinct randomized encoding. Okay, good points. So, and time lock puzzle has a lot of applications too. You can do sealed bit auction. So imagine I can do an auction where I can seal my bit and I can put it on the blockchain, and everybody can like decrypt it once the auction period has ended. And nobody can open up my bit before the auction period. It has applications to non-malleable commitments. I'll not go into this, but like blockchain front-running prevention, fair contract signing, cryptocurrency payments, and even more applications. But basically, the way it's used is like you encrypt your transaction for a certain amount of time so that nobody can read it, so they cannot perform like certain adversarial attacks. So that's like the high-level idea of like how most of these applications work. Yeah?
Do you get some homomorphic properties on the time lock commitment?
So that's an excellent question. So the construction that we have, so you can also ask the same question for a succinct randomized encoding, and like some, so our scheme does not have such properties, but like the schemes from like repeated squaring, they do have like homomorphic properties for time lock puzzles. So that's like maybe something to think about. Okay, so let me go to our results. So we get something faster and simpler. What do I mean? So we give a new construction where the encoding time can be made arbitrarily small. So like let's say choose your favorite constant, like 0.001, and you can make the encoding time t to the 0.001. So you can really shrink this encoding time. We show a generic transformation from any Laconic function evaluation scheme. And there's a caveat here, which I'll explain a little bit later. But Laconic function evaluation is what G built for me. So I'm just going to use him and use this as a black box and show you a simple transformation. And I say it's conceptually simple because there was a prior work which required FHE techniques to sort of do this whole transformation. And we made their blueprint a little bit simpler. Okay, so let's talk a little bit about this prior work. So imagine that you're given a Turing machine M, which you want to run on this input X, and it takes time t and space S. So there's going to be some space dependence here that I'm going to be concerned with. So if you want the encode time to be just independent of t, you can do this from I/O. So great, but I/O is not post-quantum secure, or at least we don't know. We have some heuristic candidates, but we don't know from well-founded assumptions. And in a follow-up work where Agrawal, Malavalta, and Zhang showed that you can actually get encode time to be square root t times s times polylambda. And they showed this how to get this from the same assumption as what G was mentioning. So it's similar to similar to FHE, modulo this noise thing, which was mentioned. So this is conjecture post-quantum secure, so maybe we're happier. But S is the space that it takes to run this Turing machine M on input X.
Oh, so you're introducing now two parameters.
Yeah.
There's one parameter, there is no saving, but there's two parameters that will be saving fast as well as squares. Sorry, squares.
Yeah, so think of like S being smaller than square root t, otherwise like this would not give you anything meaningful. Yeah. So we're concerned with like space efficient Turing machines. Okay. Great, so in this work we show that you can choose your favorite constant, and you can get to t to the epsilon times s.
I'm sorry, this is for time lock.
This is for succinct randomized encoding.
Oh, for succinct randomized.
Yeah. So succinct randomized encodings will give you a time lock puzzle once you have this like worst case.
And just to check, you're assuming like 1 bit output or small output, right? But you would otherwise scale with output length as well.
Yeah. You can think of like S-bit outputs.
Sure.
Yeah. Okay. So Laconic function evaluation, like I'll briefly sort of abstract whatever G explained as like a black box, because what we need is a little bit simpler than Laconic function evaluation. So given a function f, there is a setup which produces these public parameters, public key. Using this public key and an input x, you can output a ciphertext CT. This CT you can decrypt publicly, like anybody can decrypt it, using just the public key and the function f, and you get back f of x. Okay? So there are some properties that we need. First of all, what's the size of this public key? So there was a long line of work which G mentioned, like in his tables. Like initially we knew, so the time it will take to compute this will depend on the function f. But the size, initially it started with growing with the function. Then we had BGG plus, which were depth dependent, and then we had G's work, which was like got rid of the depth independence. But it grows with the input plus output. So there is some output dependence here. And this we can get from circular secure learning with errors, and that's the only algebra, hopefully, or like as primitive. Yeah.
So even more later work that maybe one of the work that G cited, you get rid of the M.
Yeah, you can make it M plus.
B on N.
I think that's in the ciphertext size.
In the ciphertext size, but the public key will still have to grow with the input length.
The public key can grow with L to the 2/3.
So in our case, like M and N will be the same. So maybe it's not like too much of it, but like maybe I need to check like if you actually get some like concrete improvements. I'm actually not sure. Yeah, we can discuss offline. Like, or either m will be bigger than n. So. Yeah.
Okay, I think if you have something that compresses on m, then you have I.
Yeah, so that's my next point. Anything sublinear in M will lead to I/O. So we want to avoid sublinear in M. Okay. But I think Rachel was mentioning maybe it's M plus something, or right?
I was just curious if
Okay.
it's like more advanced AB with a constant size ciphertext work can lead to some improvement on dependency on N.
Okay. Let's chat later about that. So the security says that the ciphertext should only reveal f of x. It's like a natural security property. And this is the entire like Laconic function evaluation framework that you need to know. Okay. So we'll be using this to get all the way to succinct randomized encodings. So how do I get there? I want to make the point that like this is an observation made by Agrawal, Malavalta, and Zhang, that this notion is already good enough. Like it gives you some sort of a pre-processed notion of a succinct randomized encoding. So what do I mean by pre-process? So imagine you have this setup algorithm which takes in this Turing machine M. You can also imagine it takes in like the circuit representation, but like this setup algorithm will run with the function. So it means it will take time t times s times poly lambda to run. But what it outputs is something short. It only depends on s times poly lambda. Okay? But once you have something short, you can use this in like a pre-processing. Imagine like you have a succinct randomized encoding which can pre-process and output this short public key. Now encoding is very efficient. Like this is like maybe like a decomposed property that like, you know. So now in this decomposed property, like once you see the input, because input x is like s bits long, and public key is s times poly lambda, generating the ciphertext is very, very efficient. Okay? Similarly, decryption is also efficient. I don't have it here, but like this gives you a pre-processed succinct randomized encoding. So so this is great. We have this sort of pre-processed notion, but can we do better? Can we get all the way to a succinct randomized encoding? So what we want to do is like somehow reuse this preprocessor. And so I'm going to divide this Turing machine steps t into like square root t chunks. So imagine like we have a circuit which performs square root t steps of this Turing machine, and we're working with space S. Okay? So now the setup will take this circuit, and it will take times square root t times s times poly lambda to produce. But the size is short. Size is still s times poly lambda, and you get the short public key. So let's do something before. Like let's just encrypt x under this and output CT1. So there is an issue here, because now what you've done is you reveal this intermediate computation. So once you have CT1, anybody can decrypt and output the state after square root t steps. Succinct randomized encodings don't allow. You only want to reveal the final computation. You don't want to reveal the intermediate midpoint computation. Okay? So how do you fix this? Throw encryption on top. This is like the most natural strategy. So you don't want to reveal the state, so I'll encrypt it. So now imagine that the function that I'm trying to compute is some symmetric key encryption. Okay, so what will I get out? I'll get out symmetric key encryption of state square root t. But now like I'm sort of stuck, right? Like how do I, like I need to get all the way to state of t. So how do I do this? So I'm going to output some gadget g, which I'll explain what it is later. But what do I want? I want to go from like the symmetric key encryption to back to an encryption under the LFE. And if I can do this, I can do this repeatedly, and I can move forward, and in the end, get the state at point t. Okay, so let me, so what does just this gadget do? It decrypts like the symmetric encryption and encrypts under the LFE public key. So let me show you again what do we want. So that you have some gadgets which go from symmetric encryption back to LFE encryption. And the gadgets or these will be in red, and the LFE stuff is in orange. And what we start with is an ciphertext under the LFE encryption. And you have like square root t of these gadgets. And what a decryptor will do is it will perform LFE decryption to get the secret key encryption under K1. It will use the gadget to get back encryption under LFE encryption, and it will just repeat the process again to use the gadget to get back the secret key encryption. Sorry, you use LFE decryption to get back the secret key encryption and sort of move forward. Okay? And you can imagine like the last gadget, it does not re-encrypt, so it just outputs the state. So hopefully, any questions on how the scheme will look like? Okay, sounds good. So what's the time that I've taken to do all of this? The time I've taken is square root t times to generate this gadget, the time to produce CT1, the time to generate this public key. So I know this time to generate this public key is square root t. I know the time to generate the CT1 because public key is small and input x is small is kind of short. And this depends on square root t, so there's some time. My hope is that this time to g is polylambda, time to generate this sort of gadget. And if I have, then I have a succinct randomized encoding, because what I've produced is something which takes square root t.
So somewhere the key I guess the first ciphertext also like knows the secret key K1 and encrypts under.
Yeah. So I'm lying a little bit. Like so, it takes an x comma K1 and yeah.
Good. And then the GK1 needs to know like about K2.
K2. Yeah.
It's like created.
Yeah. Okay. So what's the size? The size also square root t times g plus ct plus pk. Okay. So what's this gadget? So I'll introduce gobbled circuit. So this gadget is just going to be a gobbled circuit. So there's not going to be anything more. So what we're going to do is like we're going to just chain them using gobbled circuits. And that's pretty much our entire construction. So let me just introduce what is a gobbled circuit. So imagine that you have a circuit C and an input X. We have like this decomposed algorithm that we'll use where imagine there is an input encryption algorithm which takes an X and some key K and outputs an encoding X tilde. You have a circuit encryption algorithm which takes in the same key K and the circuit C and outputs this circuit encryption GK. Correctness says that GK on input X tilde will output C of X. And security says that even given GK comma X tilde, the only thing that you reveal is the output of the computation, C of X. Okay? So why is this sort of good for us? So first of all, it has this decomposed notion that like the circuit and the input are independent. More importantly, the time and the size to compute this input encryption does not depend on the circuit. So this is going to be sort of crucial for us to like sort of chain things together but still not grow with like sort of land into circularity issues. So the key takeaway from this is like the gobbled circuits are helpful for us because this input encryption algorithm is independent of L and C. Okay, so hopefully gobbled circuits are clear. Okay, yeah.
What would go wrong if you replace this with a reusable gobble circuit?
Okay, that's exactly the question here. So LFE implies a reusable gobbled circuit. So what if like so I have these like G1 to GKs which are in the end going to be gobbled circuits. So what if like you think like okay I'm gonna get even more compression and let's just use reusable gobbled circuits. So there the size of the public key will depend on m plus n. It will depend on the output. So here, if it's going from S to L bits, this just depends on S times polylambda. It does not depend on L. So there is no dependence on L or the circuit. So that's going to cause issues. So you cannot do that. Okay. So that's a good question. And so let me show you the full construction. So the full construction is going to be as follows. There's going to be a circuit C, which I'm going to think of. So this is the gobble circuit that I'm going to gobble. It's going to be the LFE encryption algorithm. So this is what I have to rerun the computation again and again, right? So I'm going to gobble this LFE encryption circuit. At the same time, my LFE encryption algorithm will take in the input encoding function for the gobble circuit. It's going to perform square root t steps and then input encode it. And here, if you have like dependence between if this input encoding depends on the LFE, then you have a circularity. Because the LFE is defined with respect to input encode, and if the input encode like depends on the LFE encryption algorithm, like both of them depend on each other. So it's like kind of crucial that like these are independent things. So yeah, so it's crucial that these algorithms are independent. And if they are independent, then in the end, what you get is square root t times s plus time to input encrypt. And time to input encrypt, because it's a gobbled circuit, it only grows with the input of the gobbled circuit. So it just is s times poly lambda. So everything is like square root t times s times poly lambda. Okay. Okay. So great. So we've done something meaningful. So now to just make another point. So a prior work, Agrawal, Malhotra, and Zhang also had like a similar blueprint, but they really had to use FHE, hint FHE, and like do other tricks to get this independence. And but here, like gobbled circuits is good enough. Okay. So this is the final construction. You have a gobbling algorithm as part of the LFE setup, and the time grows with square root t times g plus what I've said before, and everything is square root t times s times poly lambda. And security is also straightforward. Sorry. Where given the first two, like let's say CT1 and G1, I can simulate everything using FE and gobbled circuits and move hybrid forward one by one. So it's like very, very straightforward. Like nothing complicated happening. Okay, great. So now, how do I go from square root t times s times poly lambda to t to the epsilon time? Yeah?
Question which I assume is relevant to what you would say. So here you are using the fact that it's a Turing machine,
Yeah, so.
and not a RAM.
Yeah. So in our paper, we actually use repeated circuits for like technical reasons, but like you can imagine right now, everything is Turing machines. So if you view it as circuits, you don't have to like do a transformation from circuits to Turing machine and jump back, and like there's some inefficiency there, which we can like sort of get rid of. Yeah.
Before you show going beyond, suppose you just try to do with qboot or something else right now, what would go wrong?
So you would have, so if the LFE is qBroot, then you would have t to the 2/3 gobble circuits, right? And if you had like t to the 1/3 gobble circuits, then LFE takes t to the 2, like the public key generation takes t to the 2/3 to generate.
Yeah, I think.
Yeah. Yeah. Okay. Great. So now one natural strategy after hearing all of this is like, okay, if I want to go beyond square root, like I have something which gives me square root compression, why don't I bootstrap it, like run it over and over again? Like square root t, like will give me t to the 1/4, and like hopefully it gives us something more, right? So okay, so we have this construction which takes times square root t. What if it has square root t times s times poly lambda dependence? I run it again, okay? So what happens here? So I get square root dependence in time. So I get t to the 1/4 times square root s times poly lambda. But then I take a hit from the space. So now notice that the space is grown, right? The space is no longer s. So because the space has grown, now this is t to the 3/4. So I've not really gained anything meaningful. Okay? So how do I fix this? Well, this is, notice that the more expensive step is generating this short public key. But the size of this short public key only grows with s times poly lambda. And my hope is, if I can use the asymmetry, then I can actually get more and more beyond square root. So how do I do this? So like back to what Brent was mentioning, like here's the 2/3 version. So imagine the square root performs 2/3 steps. The circuit performs 2/3 steps. Now you're going to have t to the 1/3 gobble circuits. This operation, this LFE operation, it takes time t to the 2/3 times s times poly lambda. Takes space s times poly lambda. This is good for us. I run my square root procedure on this. If I run my square root procedure on this, what do I get? I get t to the 1/3 times square root times s times poly lambda. And now if I combine t to the 1/3 with t to the 1/3 gobble circuits, I have something t to the 1/3. Okay? So you do get s times square root s, so you get s times s to the 3 by 2. But like in the paper, we show how, like if you, this is because of like this Turing machine to circuit thing. Like there is some inefficiency here. In the paper, we explain how to get rid of this. There's one caveat here. The space must be a space-efficient algorithm. So it should not happen that the space of this, so this is not just the output. Like what we want is that the space taken during this procedure, it must be efficient. So it's not enough to just say that the output is s times poly lambda. This whole procedure of running setup should be space efficient. And as long as that's true, the whole thing goes through. Okay. So just I have a few slides explaining what what this means. So imagine you have the setup algorithm, and it takes it takes the input c and like lambda, and it's outputting something s times poly lambda. What we don't, or c times poly lambda, sorry. Or s times poly lambda is right. But what we don't want to happen is that it somehow blows up during its computation, the space what it's using, when it's performing this setup operation. And fortunately for us, like G's and construction which she presented prior to this satisfies this. So just to give you an intuition of why it's satisfied, this is going to be very high-level intuition. There's a lot of moving parts here. This uses BGG plus like lattice homomorphic style techniques. But basically what's happening is like you have some public matrices corresponding to these attributes. And you're running some like a procedure to generate this public key, some evaluation, homomorphic evaluation procedure. And this public key is going to be this A sub C, which is going to depend on this circuit C. So think of like what if C is like some like x1 or x2, then your procedure A sub C will just be A1 plus A2. And if it's x1 and x2, then it's going to be some like some matrix multiplication operation. And like you can generalize this. But the high level idea is that like instead of like working on circuits, now you're working on these meta circuits, where instead of working on something which was like bits, now you're working on some poly lambda size things, but you've not changed the topology of the circuit. So if the original circuit did not blow up or the original Turing machine was space efficient, then this new procedure is also space efficient. Okay. So we blow up a poly lambda, and like but everything else goes through. Okay, I have some open questions, but maybe any questions about? Okay. So there's a lot of open questions, and we'll move on to Julio's talk next, where he'll solve some of them. But like they're still under like a new assumption and like or like decomposed LWE, which implies the succinct family of assumption. So let me first the biggest question here is, can we improve the dependence on space? And this is reminiscent of like some of these IO works originally, which was like we originally had like something which depended on space, and then we showed how to get rid of it. So is the hope like, can you get rid of the space? And follow up, like Julia's work does this, but under a new assumption, decompose LW. What's the connection between SRE and obfuscation? That's like something which I've been thinking about, and I have no like good intuition for why this is, because obfuscation is like, you can think of it like XIO, where like you're compressing truth table. But SRE is like you're compressing computation. Like you have a Turing machine which is like running for time t, and somehow you can compress the computation time. But like, what's the relationship between these two objects? Like, we don't know. Like, a more direct practical solution for the construction that we have, or like some homomorphism would be great. Because right now it involves like this bootstrapping step, which like is like you're running things over again. Like it's, nobody would think of implementing this, or I wouldn't. So, and in our work, we also have a fully succinct. So we do get something which is fully succinct, but we are sort of like cheating. We are doing like complexity leveraging, and we are incurring a huge security loss. So we do get something which is independent of time t, but we have like a huge security loss here. But like follow-up work, again, does this from a stronger assumption than in our work.
Where is the security loss?
So you basically set it as like, instead of doing, so our transformation can only be done constant number of times. But if you can like do it slightly more than constant and set your security parameter like log lambda or something, it's like cheating, I would say. Yeah. Okay. So I think there are some excellent questions. Even after like Julia's work, I would say like just getting from like circular secure LW would be great. Like I would imagine like some of these things are doable, but I don't have a good intuition. And the connection between SRE and obfuscation, I think we just don't understand these objects very well. So, also like another one is like, can you actually use some of these things can you use an SRE to do other things that we only knew how to do from obfuscation? Like you have this tool which gives you a shortcut for computation. Can you use this for other things? Okay, that's all I have, and thanks.
You briefly mentioned this connection between time lock puzzles and like non-naive people. This seems a little counterintuitive to me.
So this is Rachel's work. Basically, they have like they show that like time lock puzzles allow you to get access along two different hardness things, and that somehow that gives you non-malloc. It's a lot of work. Like it's not immediately clear. Yeah, you should ask her.
Alright, let's thank Rachit.